Everybody has been, particularly me, we've all been waiting for this grand finale. And we thought that what better way for the grand finale better way to start the grand finale but have Praveen actually introduce Jean. So who by definition is Jean's longest time collaborator and of course, colleague, etc. So with that, I'll give it to Praveen and he'll introduce Jean.
Thank you very much, and thanks to Gustavo and Rahul, etc., for inviting me. Thank you for giving me the honor of introducing Jean. I heard, at least 2 or 3 people said when they read Jean's papers, there'd be one sentence and the next sentence, but then they had to spend a lot of time going from the previous sentence to the next sentence, even though it's perfectly clear how you get there. So you can sympathize with me when I had 2 years of meeting Jean every week. And he would write a few sentences on the board, and then I had the rest of the week to figure out those sentences meant and what is likely to come next. So, but that experience also allowed me to work better with succeeding generations of students. So I don't know where Venkat is, but he was, I think, the next one. And then there's Kostas, and then there's Andrea, and I don't know who else is here. Steve Lowe, this is somewhere over there. And so there are a lot of students, but John gave me the muscles to deal with this. Retinue of students. And so it's very exciting times, actually, in those days. And so I think you graduated in 79. And then we shipped him off for 3 years to the cold of Ithaca. So then he came back, and he's stuck now in the fog of Berkeley for the next, 30 years or so. And I hope that he continues to stay here. I was going to sort of recap some of his work. I think Kumar started out with giving the list. And I would like to go back to the first days of his PhD work, when he took some sort of known results in queuing theory, but then provided a not just elegant, but very insightful understanding of those theorems, such as the product form theorem for Jackson networks, such as when are successive sojourn times independent, and sort of non-overtaking condition, which looked kind of bizarre, but then once he explained it to me, it made perfectly good sense. And on and on. And I think then when he came back from Cornell, and I don't know when Venkat started here.
Well, multiple phases, but...
Yes. He also went to Cornell in the cold. That seemed to be a tradition.
I had a second phase in the starting in 94.
Yes, and then he went sort of short migration across the street into the mathematics department, and then returned to the greener side.
Green in multiple ways.
Campus. And so there's a period of time when he worked on bandit problems. And then John got interested in control, I think, and so there's a phase of control, which was stimulating and control of queues and network and resources. And then slowly Jean expanded, and so I lost touch. It was difficult to keep up with him. And then it came back again with this, when Jean got interested in economics. Right? And so, I mean, in between there's a lot of stuff that he did, but I'm just putting the points where I came into contact with him on a sort of technical level. And so, a period of time in economics. That was interesting to me because I was doing economics on other areas, chiefly transportation. But there are many similar issues there of congestion. So whether it's congestion in infection or congestion in security questions or just congestion of resources, like thinking about communication as pipelines. And then we got interested in, I think networking started somewhere along the line, and so we worked on this book together, which, the second edition, Andrea joined, so that we could talk about wireless, which we hadn't before. And there's so many such periods of time where we came into contact, not directly, but because of some third person. So for instance, Kumar visited for a year, and Richard Weber visited, and then, I don't know whether Kostas came back or not, but that was another such situation. Francois visited. Nick did not visit, as far as I know. But I don't want to drag on here, but simply to say it has been a delightful period of time with Jean that I've known for so long, as somebody mentioned, more than anybody else, other than Annie. And so we're looking forward to get your personal viewpoint on networking. Right.
Well, it's delightful to see old friends together. It's a special pleasure for me, and I thank you very much. I want to thank Praveen for the kind words, and also for all the words that I've heard. I had to pinch myself a few times to make sure that they were talking about me, and also that I was still alive, and that I was not attending my memory. So those events always make me a little bit uneasy, and I've attended some for other colleagues, and I have a mixed feeling about this, but nevertheless, this is very enjoyable. You must know that Praveen taught me almost everything I know, and more importantly, he taught me how to learn the rest that I did not know yet. Many people talked about style and taste for research, and certainly I got that from Praveen. That was okay. Okay, so I will try to tell you the lessons of 40 years of networking theory. Right? So it's a personal perspective. So the first question is, wow, I have 1 minute and 15 seconds for every year that I work on networking. So that's not easy. Also, there's nothing I can say that you don't know already that you don't know probably better than I, right? So this is clearly an impossible talk. It's probably too late because right, so I tried to convince the organizers that I did not have to give a talk. They refused. So, right. Okay, so I will try to give you a perspective on 40 years. And I will start with one statement. This is not my statement. This is a statement that was made to me by somebody who was a Cisco certified engineer. And he explained to me that he does not need any theory to manage the network or even to understand how the network works. Okay, which is true. Another statement. This statement was made by a colleague in 1987. He said, we have enough theory for the next 15 years. And if you count the dashes, you'll be able to recognize the name, but I will not leave you enough time. The next statement is also by somebody well known. He said, what's the point of theory? You change the assumptions, you get different conclusions. What good is that, right? You could also easily guess. You can tell it's not Venkatanantaram. The next statement, it's about one of the inventors of the internet. We like TCP as a beautiful theoretical result, understanding why it works. But he said, well, TCP slows down when it is congested. That's all there is to it. Right? So you don't need any theory to really understand TCP. That is true. It's getting easier to guess. Okay, another statement from a colleague or so. Networking, the problem is solved, right? So there is that tendency to believe that, okay, we have solved the problem, like we have solved the power distribution network, we don't need to work on this anymore, the problem is solved, it's a commodity, we can buy a network easily at Radio Shack, not Radio Shack anymore, at Best Buy, so the problem is solved. Okay, so it is indeed the case that you do not need theory to understand most of the ideas of networking, right? The idea of packet switching, of layers, internetworking, how to connect networks together to the internet. The idea of shortest path routing, well, it's an obvious idea, you don't need theory for that. CSMA is the same thing, right? It's, you try, if you fail, you try and try again, right? That's the idea of virtual circuits, VLANs, MPLS, that's also a fairly obvious idea. And then the network management ideas, like a simple network management protocol, remote monitoring, software-defined network, NFV, whatever that is, right? All that is, those ideas are innovative, they are disruptive, but they are simple. They are extremely valuable because they've changed the world, right? So we should not minimize ideas because of their simplicity. But the point is, well, you don't need theory for this. So the question then is, what is the usefulness of networking theory? And so that's what I will try to discuss by looking back over the last 4 years. Before I do that, I would like to tell you my view, my recollections of Berkeley in 1975. That's when I came. This was Berkeley in 1975. Not quite. Not quite. So when I came to Berkeley, it was no longer like this. So I thought that maybe when Praveen came, it was like that. But it has been, no, it was not like this. So I think this is the first building on campus, South Hall, I think, right? No, so this is more like 1820. This was the popular culture at the time. That was a car at the time, right? This was what was popular on TV. So it's a long time ago, 1975. The politics of Berkeley was interesting. Berkeley was a hotbed of the defense of free speech, right? And you remember in 75, it was just after the end of the Vietnam War, and just after when Nixon resigned. Right? So that tells you how much time has passed, because having to defend free speech, fighting pointless wars, and questioning the integrity of the president, those are things that will never happen again. All right. The technology was exciting, and that is what pushed me into engineering, in particular into electrical engineering. So when I finished high school, a man walked on the moon. IBM came out with their 370 computer. It was one of the big computers at the time. And Intel came out with their 4-bit microprocessor. So that was all around the early 70s. So it was a time where you believed in the evolution of technology. This was clearly the thing to work on. Right? Now, more directly relevant for me was Berkeley. What was happening in Berkeley intellectually? Well, in the early 60s, there was this famous book, Linear System Theory, a state space approach by Zade and Dessor, where they looked at the systematic theory for systems that are linear, continuous in state, and they tried to find a nice framework to understand those systems. A little bit later, there was a thesis by Pierre Brémaud, the martingale approach to point processes, and it was followed by the work of Praveen. So Wang, Dessor, Praveen, Varela, René Bull, Franz Kuppen, and Mark Davis. There was a collection of work that together proposed a scientific approach to the analysis and design of systems. Not only linear systems or nonlinear systems, but also jump systems. So jump systems are like queues, right? So there was the hope that you could analyze systematically systems that before looked very complicated by taking a systematic scientific approach. So it is in that spirit that I started my PhD. And I thought when I looked at problems, I tried to see what is the correct way to think about those problems. Okay. So why theory networking? I will make 2 points. Well, there are major new challenges that occur all the time. So at any given time you think, oh, we have solved the problems. But then very quickly new problems appear, right? So maybe the problems are with blockchains, or the problems are maybe in specialized networks like data centers or some other specialized applications. And also theory, I think, is necessary to see how to deal with those problems. Okay. To explain this, I would like to give you my view of the innovation process. When you look at a problem, the first thing that you do is that you build a caricature of the problem. So caricature means a simplified view that accentuates the key features of the problem. So this is a word that Frank Kelly used for models of systems. I like that name. So you start with the caricature. You use that caricature to get some understanding of the system, and then you come up with a scheme that seems to make sense for that caricature. Right? And then you have to elaborate the scheme to come up with a design. Right? So let's look at an example. You are trying to put something to help your car move along the road. Right? And you think about it and you say, gee, this doesn't work too well. The corners are preventing the motion. So you work on it and say, oh, the scheme, I will eliminate the corners. You come up with a round wheel. Right? And then, so this is your scheme. And then you elaborate that and you have a design. Right? That's simple. The point is that your caricature addresses a basic problem. So what you have in mind is not just this little object, it's the real system, the end system. So when you choose your simplified model, you must have in mind the ultimate goal, right? So you don't design a caricature just to solve a toy problem, at least in engineering. You have in mind a big system, but you start with a simple view. Okay, this is another example. You understand that when you see a paper plane fly, the paper plane does not have to flap its wings. So say maybe we can make something fly without flapping the wings. You come up with a fixed design, a simple scheme, and then you elaborate that. This is another example that I like. You eat a piece of chocolate. I'm from Belgium, we like chocolate, right? And then you chew on a hazelnut, and you realize, gee, those two tastes go well together. So the scheme will be to try to integrate the two flavors. So you try to experiment, and you say, okay, I will chop the hazelnuts and the chocolate, put them together. Then you come up with this idea. Okay, that's the basic idea. But then you want to elaborate the design, and you come up with Nutella. Okay.
Italian.
It's Italian, yes. Ferrero, Michel Ferrero, 1984. Another example, you look at the switching board for the phone system, and then you look at the mail sorting room, and you say, wow, these are two very different ways of routing information. Why can't we route electrical signals the way we route mail? Right? And then you come up with a scheme, which is packet switching. Then you elaborate it, and you come up with ARPANET, right? So the point is that what you have in mind is transferring information, and then you say, what is the basic scheme? You reduce it to the simplest problem, how to write a piece of electrical information. This is another example, it's familiar. You have two flows that want to share one link with rate C. Two sources transmitting at rate X and Y. And they don't know about each other. And you say, how can they somehow agree to use only C over 2 each? How do you do that? Well, a simple approach would be this switch will count the number of flows that there are. And you say, okay, there are two flows. Each one should get C over 2. This was the ATM approach or the in-serve approach, right? The resource reservation approach. But then, no, there's another scheme that says, well, if they both increase at the same rate, and then they multiply their rate by a constant less than 1 when the sum exceeds C, then this will converge to C over 2, C over 2. It will work if you have 5 connections. It will converge to C over 5, C over 5. So this is the AIMD system. So that's the scheme that you find, that you understand on a simple model. You would not understand it in a network, because in fact it does not work in a network. But it works well on a link. So you say maybe if there's only one link that is congested, this will be good enough, right? And then you elaborate that, and you come up with TCP, right? Okay. Another example. You are in your bathtub, right? And you realize that your rubber ducky floats, but you do not float. You think about it, you say, why is it? And then you understand, right? And then you use that model to elaborate the design of ships. So the point is that you need a small model, but you have in mind a complex system. Right? So the way you choose the little model is with the view of the big system. You have a cocktail conversation, and you try to say a word around the table. Well, you try, and if you fail, you try and try again. So this is Aloha, right? You elaborate that, you get Ethernet, and you get Wi-Fi. So to understand the big idea, you don't need the big system. You would not understand the big system, you understand the small system. So you get inside by looking at the caricature, and then for the implementation, you have to work more. The question is, where do you need theory? Do you need theory for the insight, or do you need theory for the implementation, or both, or neither? Well, the point is that all the possibilities exist, and I will show you examples. Interestingly, it is possible that you need the insight, you need the theory for the insight, but not for the implementation. Right? Okay, so some example. Okay, this is packet switching. Do you need any theory for this? No, you don't need any theory. It's a simple idea, it's a trivial idea. Baron Davis, 1964, at the same time as Nutella. As far as I can tell, those are independent discoveries, but you never know. Right? What is less clear is the role of Kleinrock. It's very controversial. I don't know if you read the literature, some people will say, oh, Kleinrock did not invent anything. So I went back to his thesis, the thesis proposal, in fact, 1961, 35 pages. And it is clear from those 35 pages that he had the full view of the networking. The idea that messages are sent in a store and forward way, that you do routing, that you do scheduling. You don't pick, it's not necessarily first come, first served. So he had all those ideas already in his paper. What he did not have is the idea that how do you encode a packet of information and all those details. But he had the abstract view completely already at the time. Okay. So what about this? Well, no theory is needed. This is, I could not find the original patent, but it's probably Stone, Miller, and company. Yeah. So what about this idea of AIMD? Do you need theory for this? Well, it's an easy theory, right? You draw a picture and you can prove that it will work, right? So that's Chu and Jane, very, very famous. Now, to go from TCP, from AIMD to TCP, do you need any theory? The answer is no theory. So if you would look at the paper of Van Jacobson, he refers briefly to the idea that, not to this paper, but to the idea of control. If you multiply, if you have proportional control, then you have exponential stability. So he knew about that, but he did not need a theory to create TCP, because at the time the theory did not exist. There was no way to understand the control of a network, a distributed network. Okay. now, if you want to elaborate this later, much later, you can refine TCP because of a better understanding. And I should add DC TCP and all this, but so many people have worked on this. I mean, this has been very fertile. And so you could ask, TCP exists. What's the point of going back and trying to understand it better and trying to improve it? Well, as Mohammed said, well, when you're in a data center, the conditions are very different, the objectives are different, you need a different protocol, right? So there are many situations where you need different protocols because the objectives are tighter and the conditions are changed. So you go more for optimization and less for universality in that nice way of explaining. This is an interesting question. So we do not route typically packets one by one. We route virtual circuits more and more, right? So you route flows. And if you have two links, you want to balance the number of virtual circuits on the two links. And then you could say, well, there are two obvious schemes. One is that when a new flow arrives, I choose a random direction, a random path. The other approach is that, well, I will route the least busy path. Does it make a difference? Well, it depends on the assumptions that you make about everything, right? But under reasonable assumptions, you find out that if you look at the average rate per flow, it doesn't make a difference. Average rate per flow, what I mean by that is that if 5 connections use this link, with TCP they will get a fifth of the rate of the link each, assuming that, right? Assuming TCP is perfect. So it turns out it doesn't make a difference, and I could elaborate on why. But you understand that from the caricature, so at that point you say, well, maybe I should not try to implement this option B in the network, which is much more complicated than just random route. Okay, there is related work. It goes back to work with Tony. Tony, if you visited us in 1982 or 83. Tony.
I was second year, so 70.
Oh, 79. So, but in any case, we wrote a paper on a simple routing problem, right? So a lot of work and by many people on routing. It's still the idea of dynamic. Is it worth doing dynamic routing or not? Should you do randomized routing or? A related story is the work of Frank Kelly. When you say, well, at the time he was looking at the phone calls. Okay? When I want to route a phone call from this point to that point, I take the shortest path, right? But maybe that path will be busy. Then I will take an alternate path. So what happens if you do that? Well, if you analyze the system, you discover some metastability. What is happening is that if it's a bit busy, then many connections will not find the shortest path. They will have to use an alternate path. They will use more resources, so the network will be exposed to a load that is much larger than it should be, and then you will stay congested for a long, long time. And then congestion will go away, then you remain stable for a long time, where every connection finds short as well. Then you will go back because of fluctuations. For a long time you'll be congested and so on. So you look at that, and then you say, well, I discovered the problem on this simple caricature. What is the solution, right? And the solution that Frank came up with is the idea of trunk reservation. He said, let's use an alternate path only if there are enough free paths. If not, we save them for the direct connections. Simple idea, but you avoid this metastability. So this is another example where the insight that you get from a very simple caricature is applicable to a big network. So he applied that to the British telecommunication network. It works. All right. So another example is this. Okay. So we said that to do the slotted Aloha, the theory is very easy, right? It's something that you can explain easily. So here I have to clarify what I mean by theory, because what most of us mean by theory is not what Venkat thinks of theory. So by theory, I mean that you have a mathematical model that you use to understand the system, right? To get some properties of the system. I don't qualify the theory that I need. I don't say I need the concentration inequalities or anything very complicated. Right? But the process of having a mathematical model of the situation. Hilbert space, right? Yes, well, you could ask Andrea, give me a space that is not Hilbert. Okay. So easy theory, but powerful. Now, when you want to go from this model that works well for sharing one link, one radio channel, to a multi-hop ad hoc network and see if that still works, there is a lot of work needed. There you need theory, right? So it's the same as going from AIMD on one link to stability of TCP in a network. There you need a lot of theory. So here's some beautiful work, and I'm very happy that Libin, where is Libin? Libin is there. Libin could join us here. And of course, work by many colleagues trying to understand the properties of those systems. Okay. This is an interesting question that Kumar worked on. He said, okay, you have a collection of radios, and you want to go from one radio to the other radio. What should you do? Should you transmit as far as you can to reduce the number of hops that your packets have to go through? Or should you be very polite and take many small hops? And if you think about it, it's not obvious, right? Because there is a tension. Here, you save the number of hops. There, you have less interference with you create less interference with other flows. So there are some pros and cons. What is the answer? The intuition will not tell you, as far as I can tell. You need some little calculation. Well, some non-trivial calculation. So theory gives you the insight. It tells you, well, maybe depending on the situation. So if your network is dense enough, you should, if there are enough flows, you should be polite. You should be polite. Oh, sorry, I did not mean to. So the Gupta-Kumar paper, related work by David Say, with somebody here, David, and collaborators. So those are examples where the basic questions, the basic scheme that you should use is not obvious. And you have to extract from a simple model the correct insight to understand what is the right model. All right. Another example that is striking in transportation system is this Brace paradox. And what it says is that it could happen that if you build a new road, the delays will increase in the network, which is very surprising. You could say that if I improve the infrastructure, everything will get better. But paradoxically, because the drivers are self-interested, they do not try to optimize the social welfare, they don't care too much about the other drivers, this leads to this paradox. So this is called the so-called price of anarchy. How much do you lose because the people are making independent decisions, right? Everybody loses by making independent decisions, even though they all do a decision that seems to be better for them, right? That's why you need regulations, that's why you need laws, that's why you need politics. So you need some theory to really understand what is happening. And this theory has been elaborated by many people, including John C. Siklis, Ramesh Johari, and Balaji. And Balaji has looked at incentives for people to do the right thing, right? This is another example that I like in networking. So this is based on the Paris Metro caricature, where you have many cars, and you decide that some cars will be first class and will be expensive, and the other cars, the same cars, will be cheap. So what happens is that the expensive cars will be less congested. Therefore, they will be more comfortable, which justifies the higher price, right? Even though those are the same cars. So you get quality differentiation not by different technologies, but by pricing, so which is quite interesting. Now, network neutrality gets in the way of ideas like this, but that's another story. You don't need theory for this. This is obvious code. But those ideas have general value that you understand from a simple model. Another story in networking is the idea of free riding. So you have people rowing, right? And then you are in the middle, you say, well, I will let the other people row for me, right? So this is free riding. And as a result, everybody will row a little bit less. Okay, so that's a simple idea. But then the elaboration of the consequences of this free riding in particular situations requires some modeling and some analysis. So the fact that people will invest less than optimally in security because they rely on other people having their virus protection, and so they say, I don't need it, maybe. So some very interesting work by many people here. More generally, the idea that security is a game. It's a game between people that attack and people that defend. So this game theoretic view leads to ideas that show that maybe the most vulnerable part of a network when it is subject to attacks is not the same as when it is subject to random failures. So there are strategic aspects of the network that can be exploited and that leads to a different conclusion. So Hassan, thank you for being here. It's a nice work with John Musacchio, who is also here, and Venkat, of course. Yeah. This is a famous problem, right? You have two queues that can be served by two servers, and what server should serve what queue? What do you do, right? So that's maximum weighted matching. So a very nice theory that started with Tony and with Tasiulas. So the implementation of that into routers, it turns out to be too difficult. It's too difficult to compute the maximum weighted matching. So you need a good heuristic, right? And the heuristic did not involve theory, not much. It was inspired from the idea that if you do round robin, it's better than doing random. So then this was done by Nick. Okay, now what happens? So it's a simple caricature again. What happens if you don't know the rates of service? And not knowing the rates means in a data center that you don't know, for example, the length of the jobs, how long it takes to process the jobs. So what do you do, right? One simple idea would be to say, well, I will learn the rates as I go along, right? I will adapt, and then I will do maximum weighted matching based on the estimated rate. So if you study this simple model, you discover that it can go unstable. So certainty equivalence does not work. So you need some theory to understand that, right? And it's not completely obvious. And that's work by Ramtin, by Yuan Zhang. And of course, it relates to the work on bandits. How do you choose a channel, right? Some very nice work by Raoul. And it goes back to other work with Praveen and Venkat. And Vivek Borkar also looked at some of those questions. This is a similar story, except that we are looking at a processing network. So where you are assembling parts, and then you assemble those parts, and then they keep on getting assembled together, right? And you have servers who can work on different tasks. And the question is, well, when should you activate one task versus the other? So you look at the queue lengths and you say, well, can I do some kind of maximum weighted matching? And at first I thought, yeah, that should work. But it does not work. You need a new idea. And the idea is what Levin came up with. He said, well, you have to look at virtual deficits. So what is happening there is that, let's say, I have a part here. I need another one to combine them. But let's say that I have only one part here. So I will pretend that I have another part. And then I will say, I will create a deficit. And you keep track of the virtual deficit. And you do that, then you do a maximum weighted matching, but based on the deficit queues instead of the actual queues. It's some theory, and it will show that you will stabilize the system, and that works for a network. You can also use that to maximize the utility of the flows, of the parts that you produce, and so on. Continue. So Liben, Don Tasley worked on similar problems of controlling processing networks. There are many other examples. So ramp metering is like a flow control for transportation networks. And first you think about it, does it make sense to make people wait there instead of waiting somewhere else? What's the point, right? They might as well move along. But it does make a difference. It's, some theory will show you, ramp metering is a good idea. And then you want to elaborate that into a design. Then you need to control the complex system. That's not obvious. You need some theory. So Praveen, Ramtin, and other colleagues that I don't know all of them, but so So starting with a simple model, you convince yourself the value of a scheme, and then you try to generalize that. This is another example. It has to do with jobs in a data center, as what we were reminded. Jobs arrive as a directed acyclic graph of tasks. Right? So here, what does it mean? I produce something, it produces two results that are processed, and then the two results are put together by another processor. And we assume that we have servers. Maybe this server 1 can work on these 3 tasks. Server 2 can work on the 2 tasks. So this is a model of one job. But imagine that you have a flow of jobs that arrive. So at any given time, I will have a collection of jobs that are partially performed. And some of them will be in state 1, in state 2, 3, 4. Right? So I will have queues of parts that I have to process, right? Subtasks that I have to process. How do I do all this, right? And what if I don't know everything about the processing times and so on? So then the idea is to look at some backlog energy in the system, look at the gradient algorithm, and you come up with a distributed scheme that will stabilize the network. So you have some adaptive server allocation in the data centers that in theory will prove that it works. So this is some work by Ramtin and by Yuan. Okay. I don't have time to elaborate all those examples, right? How does congestion build up in a network, right? You need theory to understand which queues are most likely to build up. Is it a combination of queues that build up, or what is happening? So, and that led to ideas of effective bandwidth, quick simulation, quick estimation, pricing, and so on. So some work by many people, Shyam Parekh, I should mention, Costas, Richard Weber, many colleagues, Georges Kesidis, this is earlier, right there, yes, and Gustavo, and Takis, and so it was fun. But again, we started with 2 queues, or even 1 queue. You look at 1 queue. So 1 queue with arrival rate lambda and service rate mu. How does it build up? What is the most likely way that it will build up? Well, it will build up as if the service rate was lambda and the arrival rate were mu. So, shockingly, right? The most likely rate of growth will be mu minus lambda instead, right? Why? Right? And then you say, what happens when I have 2 queues, or 3 queues, right? That's also a lot of fun. Then you can look at large deviations in complex processes, where the large deviation can be a conspiracy, like cholesterol building up in your system, or it can be a catastrophe, like a cancer. Right? And there are processes that have those 2 features. Their rate can become abnormally large, or they can make jumps that are abnormally high. And then understanding when bad events occur in those systems is very intriguing, and there's some beautiful work by Venkat and Morka. Okay. How do you compare stable policies? There are many policies that stabilize network. How do you compare them, right? So you need some theory. There's very nice work by Nick Mambos on how to compare all those policies. What if you use, instead of maximum weighted matching or QCSMA, you do simpler policies, like the stability of the longest queue first. So I serve the longest queue, then if I can serve another queue in parallel, I serve it, and then maybe I'm stuck, right? So will that be stable? That was very puzzling for us for a long time. Antonis understood the structure of the networks for which this would be stable, and showed examples of when it is not stable. So I think, again, starting with a simple caricature. Is maximal matching instead of maximum weighted matching, is that stable? Right? That's much easier. I want to serve 5 queues in parallel if I can. I don't care about the queue line. Will that work? Well, no, it does not work, and Venkat came up with a beautiful example that explains that. So the power of simple caricatures. Should you do time of day pricing, or should you have pricing that is based on congestion in a very real-time way? Does it make a difference? Well, John showed that no, for large systems, time of day pricing may be good enough. There again, you need some theory. It's not obvious. Right? Network neutrality. What is the cost of network neutrality? What do we lose by preventing Netflix from paying your last mile provider? So Netflix pays their direct provider. They are not allowed to pay their end provider, what do we lose? Would the customers be worse off? Would they be? It's not obvious. So some very nice work by John and Galina have explained when it is better to let Netflix pay the end provider. Why is there a problem with cyber insurance? Or how can you make cyber insurance an effective market? That requires also some careful modeling and analysis. Some very nice work by Galina again. Okay, the game theory of security, beautiful work by John. There he was looking at a nice question where how aggressive should the intruder be when it tries to penetrate your network? If he's too aggressive, he will detect it. Right? So what is the optimum strategy for the attacker and for the defender? Where do you should set the threshold for detecting? Where do you set the level of aggressiveness? Very, very interesting ideas. So network vulnerability, I already talked about it. So the challenges. So that's a review of my view of innovation. Start with a simple understanding of the problem, then try to extend to the design. So the big question in networking is networks are complex, and you want to control them. Right? So you monitor the network, and then you control, and you make decisions. What information should you collect? So I give you an example where knowing how many connections there were on different links was not helpful. You do not need that. So there is a lot of information that you could collect. Most of it is not useful. To find it out, you need some careful thought experiments to really analyze the basic effects. Right? What do you control? How should you learn? Because you don't know the many aspects of the system. Right? So many questions. This is an example of the DARPA program where they want to have radios that share the spectrum in a fair and efficient way, but they are not co-designed. So you want to limit the role of standards because they slow down innovation. So what should those radios do? Right? What should they sense? What should you control? What do you adjust? Those are we have been working with Anant on that problem for almost 2 years now. It's really challenging, even at the conceptual level. It's totally not obvious. Another challenge is processing networks. Well, we talked a lot about communication network. In the panel, they said, well, computation, so the processing is the focus of networks. Data centers are certainly an example. Manufacturing networks. How do you improve the flow of Tesla trees coming out of the plant, right? And that's not a simple problem. Hospitals are a processing network. I've worked a little bit with hospitals, and they are way behind in terms of logistics, task allocation, resource allocation, right? So there's a lot to be done. The service industry more generally, right? So those are, to me, important networks for that beg for some good understanding. All right. Conclusions. Okay. Theory provides insight for new schemes. How should you queue, right? What should you? How do you schedule? Should you schedule in each node? Should you do flow control? So should the quality of service be done by having different classes of service in the routers, or should you do it end to end? Not obvious. Should you look at your queues, the neighbor's queues, all the queues? What is the information that you need to control the system? Should you optimize? Should you do simple schemes like trunk reservation? Should you time of day pricing, token pricing, dynamic pricing? What are collaboration signals among different entities? What is the minimum information that you need to exchange, right? What about incentive compatibility? How do I know that the information I get is truthful? It's not. So many problems. But theory also provides design tools. So not only getting insight, but also tools, right? So there are many examples of this type. Right? So conclusion, networking is not done. We have had a much improved understanding in the last few years for some types of problems, but there are many complex challenges that remain to be solved. The clean theoretical insights should not be obscured by the details of the technology. Many networking courses are alphabet soups, right? Understanding networking is not understanding details of protocols. It's understanding the high-level principles, I think. So keep up the good work. We need your insight and we need your innovations. Most of the good work is by the people in this room. I will, if you will indulge me for 2 minutes, I will make some final remarks, very, very brief. I'll say it has been quite a trip for me. I thought I would stay 9 months. When I came to Berkeley, I wanted to come for 9 months. It has been 43 years. I want to thank all the funding agencies for their support. Right? I want to thank my industry friends at Odyssia. Is Ayman here? Ayman is there. Terablaze, Roy is there, right? Danny, Shankar is not here. Orgo, so Ayman is there again. Right, so, the amazing colleagues and students. For the fun times, working with you has been a lot of fun. And also for putting my name on your papers. It's quite a gig when you think about it, right? Okay, I want to thank my family and friends for the encouragement, of course. I want to thank specifically for this workshop. The organizers did a wonderful job. Thank you for selecting the speakers. Except for the last talk, they were all very, very good. Right? I want to thank also the Simons Institute. I want to thank ARO for contributing to this workshop. I want to thank Annie for tolerating my wasting addiction to research. I used to say that I was living a life of self-imposed misery, but Annie does not like that. So. Praveen for preventing me from becoming a depressed, drunk, washing machine repairman, which was a much more likely outcome for me than going into academia. Praveen, I'm very grateful. So thank you all very much. Thank you. Thank you very much. So I hope that the dinner will be good, but I have no control over that. So.
Blame the organizers.
Thank you very much for this beautiful talk, John. So at this point, there's a plan to take a group picture.
Yeah, so we don't really know where to go, so we're just going to go right out there and squish you all in, and hopefully take some photos. Is that a good spot? Whatever you say.